No, I switched back to this period of recording. Yeah. All right. Let's see. Okay, so yeah, we're going to talk about probability. And so this is a specific type of probability called a binomial distribution. So we're going to look at it, go look at the example, and then we're going to do these with the calculator. So make sure you've got a calculator near you, on you. If you don't, I'll show you one. See.
I hate this whole press to test mode.
Yeah, I do
Is there a
too.
way to turn it off?
No, I tried, and it's like I screwed myself over at the beginning of the year by following. I don't know why they even told us to do it, but
You can reset the calculator, but I don't know if it does anything.
it doesn't do it. Yeah. It's unfortunate. Okay, so let's try this out. Let me just look at this as if we were doing a probability problem, and then I'm going to show you what it would be done by hand, and we'll talk about the calculator part, and then we'll look at identifying them. So what we have, 80% of the graduates of this high school apply to Penn State are admitted. So last year there were 6 graduates from Northeast High School who applied to Penn State. What's the probability that 4 were admitted? So what's the percent chance that what's the probability that 4 out of 6 of these students were accepted if 80% is like our probability year to year, person to person, or whatever. Okay, so let me just kind of go through this as if I was thinking about this by hand. Oops. So 80% for like one person. There's not really a ton of room on your paper, so maybe write this up top if you want, or just kind of pay attention. Or actually, this other paper I gave you, you could like write it on there, because we're not going to do as much on this paper. So, okay, so like 80% is like for one person. I've got 6 people, and I'm going to say that 4 of them, we're just going to look at A, 4 of them were admitted. So what I'm going to do is I'm going to multiply, because like think about flipping a coin. It would be, the probability of 2 heads would be 50% times 50%. So I'm just going to multiply the probabilities. So it'd be 80%, but then I still have 2 other people that applied, and
Would that be 0.2?
yeah, they didn't get in, so that's the 20% chance that those people didn't get in. So that's 6 people, 4 of them got accepted, 2 of them didn't. Here's the odds that they got accepted. 20% is the odds that they didn't get accepted. Okay, let's see. So this was but I copied it for the key here. So when you multiply that, you get like 0.016. So like a 1.6% chance of that happening. But this is only one of those possibilities of like 4 out of 6. So I made a little spot here. So this is people that were accepted. This is people that didn't get accepted. And that's only one of the however many different possibilities there are of this. So like example, here's another possibility. Like the first person got accepted, second person, third person got accepted, this person didn't, this person did, this person didn't. So like that's another one that has the same 1% chance. Does that make sense?
Mm-hmm.
Like just different. So then how many different total options are there? And I have to multiply those. So since we're not gonna, you can do it by hand. I'm just not worried about yes, ma'am.
Does it change the percent that we get?
So no, this would be 80% times 80% times 80% times 20% times 80% times 20%, which is still 0.016. So all these have the same thing because it's just multiplication. It doesn't matter if you do the multiplication here or here and here. Okay, so what this is actually, it actually goes back to something we briefly talked about randomly in geometry, where, do y'all remember, I used to make a corny joke about like, y'all would go to the movies and like there were so many different seats available, and like how many different ways could I sit next to a person, and it was like, this is the one option that I want to sit next to you. Do you remember that? It was a really corny joke back in so anyways, it is like a combination. Like, how many different ways can I arrange 4 out of 6? So what it ends up being, it's like a combination. So the way it would be, it'd be like 6. How many ways can 6 choose 4? On the calculator, there ends up being, oh, it's not 10. Pretty sure it's 15 different ways. I could write out 15 different options. So that's like, for example, let's do like a really easy one, like flipping a coin 2 times. All your options are this: heads, 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 tails, tails, heads, tails, tails. So like 4 out of 6 has 15 different options. And it gets pretty ridiculous when you start talking about even like 7 people, 8 people, 10 people, 15 people. There starts to become like thousands of different ways. But I'm not too worried about doing it by hand here. So like there's 15 different ways. I'm multiplying this odds. All of those have the same odds. So then I multiply it. What this is called binomial distribution. It is when we have like a fixed percentage, like 80% chance of being accepted, and a fixed number of trials, like 6 people. How many ways can 4 out of 6 have 80% chance, and they all have these certain outcomes with them. So what this is called a binomial distribution. There's definitely a way to do by hand. We're just going to do calculator to make it simple, because it's allowed to do. So let me go through what makes it binomial. So this is where I'm going to use this other page, actually. So this other one, I kind of changed it up the other day thinking about it. I was going to do this page as like our notes, the other one is assignment, but I think the other page has better examples. But we're going to use this to talk about what is binomial. So a binomial distribution. So it's probability. It's a special type of probability when you have it. Okay, so let's look at, there's 4 qualifying things that we're looking for. So maybe I'll write those out. So there's, of course, a statistics acronym, because we love acronyms in statistics to remember things. They're the best. So the acronym is BINS, B-I-N-S, even though my N there is pretty bad. Let's talk about what this means. So B means binary, and bi means 2. It means like there's 2 options. Like, is it this or did you get this? We're wondering, did you get accepted to Penn State or did you not get accepted? Did you get COVID or did you not get COVID? Like, did you win or did you lose? Did you get heads or tails? Like, is there a did you get this or this? There's 2 options. Huh?
Can it only be 2?
Yeah, we're just caring about like, did you get this or not? Now that can be like rolling a dice. All I care about is, did you roll a 2?
Okay.
And if you roll a 2, you win. So did you roll a 2 or did you not? So B means like, I don't even know how to put that. Like, basically there's 2 options. So 2 options, and basically, I don't know, maybe I'll just do the example here. So like on this, a manufacturing process produces on average 5 defective items out of 100. Quality control randomly samples 60 completed items each day and inspects them. Does this inspection constitute a binomial random variable? Okay, so are we looking for like, did you get this or not? In this case, it would be, is the item defective or not? So like, does it work basically? So is it defective or does it work? So 2 options. Does your thing have 2 options that it's looking for? like a winner and a loser, or whatever. Don't have to think about it like that. Okay, on this one, the I stands for, are the events independent? So, is each item that you're looking at independent from the other one? And so, a way that we're going to check that, an easy one is like, you could think about independent like a coin flip, but one way is like with people, sometimes our actions aren't independent from each other, or like maybe this manufacturing process isn't independent, but one thing is if our sample is small enough, then, so like let me think about this with Bryan High. Like Bryan High is 2,500 people, something like that. If I sampled 20 of those people randomly, the chances are I'm going to get a good mixture of different people. Now, like if I only sampled this classroom or something like a smaller set, or let's say I sampled 1,000 out of the 2,000 people at Bryan High, that's too big. Like then there's too many people. There's too many like friend groups that maybe aren't independent in thought or whatever. So one way to check for independence is your sample, so this is what we're going to check, is your sample taken less than 10% of the population? So if it is, it's small enough to allow for all those different variations in a day.
That's the only way to be independent.
That's not the only way to be independent.
So you want it to be less than 10%?
You want it to be less. So you don't want to take too big of a sample, because then, like,
There's too many variables.
if it's too big, so like the easy one is with people thinking about Bryan High, like if there's too big, the chances are I probably got like people, independent means like your thoughts are affected by someone else's. And so if it's too big, I probably got a lot of people who are friends and talk and think the same way.
Okay.
If it's small enough, I might get these subsets of like a freshman.
But how do you know you're not just getting like one friend group?
Because hopefully I'm doing a good random sample.
Okay.
Yes. And the thing is, a random sample, sometimes it could accidentally get an entire friend group, but if I do many good random samples, it'll be
narrow it
unbiased.
out.
Yeah, it'll be unbiased in the end. So we want our sample to be small enough to allow for variation. It's kind of weird. Normally you would think big. So in this case, our sample was 60. So the way we represent sample is with n equals 60. And so sometimes you have to be generous in your thinking of like what was happening here. So like, do we think that 60 is less than all the items that they produced at this manufacturing thing for the day? So unless it's like a car company, I'm sure, like let's say there's like a toy or like a small little part. They probably made more than 600 items that day. So what we're gonna, sometimes you have to assume independence here if it doesn't say. So like in this case, I'm probably gonna assume that this manufacturing place made more. So 60 is less than 10%. That would mean that we would need times 10, we'd need to be 600 or more items were made that day. Which I'm gonna assume that. So what I'm gonna say is like 60 is less than 10% of manufactured items. And like it's pretty common practice for the AP test to assume that. Yes.
So we don't look at the 100 at all?
Yeah, so what this is, we're gonna get to this. So 5 out of 100 is like your probability, your percent chance is 5 over 100. So yeah, that doesn't, sometimes it does give you the sample, but in this case it told us like we did the sample. Yeah. Okay, so let's kind of go back. So binary is, I was looking for a defective item or if it worked. My samples are independent because it's small enough. I'm assuming, and sometimes you do have to assume, that like this manufacturing plant did it. If I was actually doing this, I would want to make sure. And then let's see, so N is a fixed, so N in statistics is like your sample. So N in this case is talking about our sample was like a fixed number of trials. Like we were talking about 60 items a day. So a fixed number sampled. Which on Monday we're going to talk about what do we do when there's not a fixed number. We'll do that distribution on Monday, but today or Tuesday. But today we're just going to do a fixed number. So like in this case, it was N equals 60. And then I've always wondered why S. I think it was just to make an acronym that actually made a word like N's, but I don't know. Maybe I should make my own acronyms, whatever. But S is like what it stands for. So to make it like S is like, do we have the same probability throughout? So like, does each item that we're saying like, is our probability fixed? We're talking about probability here. And so the probability they said was 5 over 100, which is 5%. So yes, we had a fixed probability. Every day, every item that's made has a 5% chance of being defective. Which that feels kind of high, but that's what they gave us. So this is a binomial because it goes through these little options here. Okay.
And we can only like use like the binomial distribution like process if it matches all of those.
If it fixes these, yeah, if it goes with these. So like if I was rolling a dice and I wanted to know the percent chance of getting a 1, 2, 3, 4, 5, and 6, like I didn't separate them, then this would not be binary. But if it said like, what's the probability of getting a 1, 2, 3, or I don't know, like if it clearly like you won, you win the game if you get this and like this. So binary is this one or two options, checking independence. Independence is sometimes you have to assume things, fixed number of trials, same probability. And the reason the probabilities are the same is because of independence. Like that's why the probabilities stay the same. It's because we're saying that each event is independent from each other. Alright, so a long way to, let's go back to this one and let's try and look at this and let's see if it's binomial first. So on all of these, I want you to check, you'll see my key later, on all these I wrote out like bins and I wrote that it was checked off. So for example, maybe I'll do it up here since I've got room. So maybe I'll check my binary, like were we looking for a certain outcome or not? In this case it was, were you admitted, oops, that is totally, I just can't spell in the morning, admitted, 2 Ds, I've never spelled this bad in my life.
This is why you have to record in the next class, so you can spell.
See, but then I'm just beat down by lunch. I feel like I'm more fresh in the morning, but then I make spelling errors. Okay, anyway, admitted or like not, whatever. That's typically what you want to say there. Let's see. maybe I'll do a different color here to kind of stand out. Are the events independent? So, was 6, so we're on independence, it is our sample less than 10%? So our sample here was 6 graduates applied to Penn State. So is 6 less than, in this case, it's talking about graduates from this high school who applied to Penn State. So we kind of have to assume here, is 6 less than, this probability, 80% of Northeast are admitted. This is talking about like all time, like every year there's 80% chance. So is 6 less than 10% of Northeast high school people who apply to Penn State? So the threshold is like 60. I have no idea how long this high school's been around. We're gonna have to do some assuming here. So what I'm gonna say is like 6, maybe I'll say it up here, like assume 6 is less than 10%. Maybe I'll say like NHS apply to Penn. So I'm gonna assume that there are 60 or more people throughout this high school that have applied to it. Does that make sense? Independence is like the assumption part. Most of the time you have to kind of see if it kind of gives some leeway to it there. Alright, let's do another color. So N is our sample fixed sample. It'd be yes, like N equals 6. And then S is they're saying that the probability is 80%. So that's the probability. And they're independent, so they 80% chance for every single student. Checking those. Okay, let's try it out. So what's the probability? So I'm going to also practice just writing these in notation. So yeah, just to get in a good habit of like, sometimes they write it in notation, sometimes they write it in words. So what's the probability that the event X, so they generally just call X the event that happened. The event is 4 people were admitted out of 6. So what's the probability that X equals 4? That's our question. What's the probability that if 6 people applied to Penn State, that of those who were accepted, it was equal to 4? All right. Long way to go around this. So what we're going to do is we're going to grab our calculator, and I guess I'll pull it up for the video here. And then I wanted to do some examples, because really once you get the hang of it, it's really not crazy. Okay. So let's look at this. All right, so what I'm gonna do, I'm in a calculator page, either in document or calculate, it doesn't matter. I'm gonna click menu. So menu. Oops, that's not right. Wait, oh, am I not in a calculator? Add calculator. Okay, maybe. Okay, now, yeah, so menu, once you're in a calculator, we are statistics class, so we're going to go to statistics, which technically this is also in probability, but let's just do everything from statistics. So statistics, and we're doing a distribution. So this is a binomial distribution. So I'm going to go to distributions, and then normal, inverse, something called chi-squared, which you might have already seen in biology. And then down here, way at the bottom, it says binomial PDF, binomial CDF. So do y'all remember from normal? Do y'all remember what's the difference between PDF and CDF?
Continuous versus.
Yeah, C is like cumulative distribution frequency. P is, don't ask me what the P something, but it means one. Like P means equals this. CDF means a range. So which one are we doing here? This is a specific thing, so this is going to be a binomial PDF. So that's the one I'm choosing because it's equal to 4 is going to be the PDF. Alright, so let's see what pops up. Binomial PDF. Alright, so number of trials was 6. What's the probability that we're of our event happening? Which sometimes you got to be careful. They might ask you a question of like, how many people didn't get in? Which you'd need to use 20%. But in this case, we're looking for 80% of people got in. So, oops. Is that? I swear I'm typing 8. Okay, yeah. And then the X value is the event that you're looking for. Which it says not optional, or it says optional because if you don't click it, it'll give you the probability of getting a 1, 2, 3, 4, 5, 6. It'll give you all of them if you wanted it. But we're just going to look for 4. Yeah, you can't really see it on the screen. It's pretty bad. So number of trials, probability of success, X value. Click OK. And you still can't really see it. It's like
1, 2, 4, 5, 7, 6.
Yeah. So let's do 3 decimals. That makes it like 24.6% when you write it out as a percentage. So let's do 3. And let me tell you what you need to write down for proof on, like, to actually show your work. So what you need to do is you write out what you put, and then you just put, just like what we did for normal PDF and CDF. You just write out like what you put in there. So it was 6.84. So make sure to show, not showing your work, showing that this is what I was doing. This is a binomial. I've already shown up here that I'm using binomial, so I'm going to use it in the calculator. 0.24, did we say 6? Yeah. Okay. So let's think about it. There's a 24% chance, about 25% chance or whatever, that 4 out of 6 of those were admitted if there was an 80% chance of success for every single one of them. So that's just what this is saying. Okay. I had thought about talking about the mean and standard deviation first, but I've already gone past that. So we'll just move on to B and then we'll go down. So B, the thing is, what is the probability that more than 4 were admitted? So I'm going to write this just so that y'all see it with the notation, and it's a good habit for you to do too. What's the probability that your event is more than 4, greater than 4?
Nope.
Yeah.
What was the 0.24 what we put in the mean of distribution?
No, it's
No.
not.
Okay, we haven't got there yet.
We haven't gotten there yet.
All right.
Yeah. I should have gone there first, is what I was thinking before the day, but we'll talk about it.
All right.
Yeah. Okay. What's the probability that our event was more than 4 were admitted? So that's just basically saying what's the probability that we're 5 or 6 were admitted. Alright, so more, we're looking for a range. So we've already proven that we're in the binomial universe, like by showing this. And then more than a range is going to be CDF. So more than means cumulative distribution frequency. Alright, so maybe I'll go ahead and then I'll show it on the calculator. On your calculator, when you do this, so you go to stat, distributions, scroll down to B, it goes NP lower upper. So number of trials is 6. Probability of that happening that we're looking for is 80%. That's our event. And then what's the lowest value? Like you're looking for a range. So what's the lowest value? In this case,
more than 4, so it could be like 5.
yeah, so it does matter. Like if it was greater than or equal to 4, then you do 4, but it's 5. So you do have to be careful there. There's always mistakes. And then the biggest value
6.
is 6. Like that was the amount of trials. So 6. I don't think the calculator would let you do more than 6 because you've shown that 6 is the biggest. So let me come over here with the calculator. So menu, statistics, distributions, binomial CDF. You've got 6, 0.8, 5 to 6. And then you click OK, and there's a 65.5% chance of that happening, so 0.655. So showing what that means. So 0. So there's if it asked you to, or I guess it wouldn't in this case, but the interpretation is there's a 65.5% chance that more than 4 of the 6 students from Northeast High School were admitted to Penn State. Like that's what's happening here. So there's a pretty good chance that more than 4. And that makes sense with like an 80% success rate. Alright, so I should have talked about mean and standard deviation first because this is talking about like how many do we expect to be admitted out of 6 if there's a probability of 80%. So let me clear this. Let me bring this up. And I should have given you the formulas too. Here, we got pass those around. Grab one, pass them around the room for me. Let me bring it up on the Schoology. So I'm giving you the formula sheet that talks about mean and standard deviation. I'm going to pull it up here on Schoology. All right, so here's your formula sheet. On section 2, there's like a box. Oh, y'all's looks a little different, doesn't it? I need the 2021, whatever. There should be, where's y'all's? Oh yeah, it's just not in a box. It says probability distribution and it says binomial. So it's still the second thing on the formula sheet. You can see it says a binomial distribution. And then how do you find the mean? How do you find the standard deviation? So the n is the number of trials, p is the percent chance of it happening. And then there's standard deviation. So let me look at our problem in this case. So the formula says the mean equals n times p. The mean is, another way to say that is how many people do you expect to get admitted in this scenario? So if 6 people, the mean's pretty straightforward. If 6 people were applying and there's an 80% chance, you just do 6 times 80%. That's how many people I expect on average. Over many, many trials, I expect, what did I get today? 4.8. So you expect, so what that means is basically, you don't have to write it in words, but I can. So what that means is you expect 4.8 out of 6 students to be accepted. I know you don't have this much room on your paper, but that's what that means in words. What do we expect? We expect if there were a ton of people, of 6 people admitting, we would expect 4.8 out of 6 of them to be accepted. And then let's see. Standard deviation on the formula chart says square root in P 1 minus P. So then this is going to give us our typical distance from the mean. So you do square root 6 trials times 80% times 20%. 1 minus 80% is 20%. So, number of trials, probability, the opposite probability. And that's going to give us, this is going to give us our value that we expect to have a typical spread around the mean, from the mean. So plus and minus the distance around there. Let's see. The other day I got 0.98, hopefully. Mine was rounded. 0.98. So basically, we expect, so the reason I kind of wanted to do this first is because we expect 4.8 students out of 6 to be selected, but it could plus or minus to like 4 or 6 students, which is why our probabilities were pretty high on these up here. 65% chance, and this one was like, what, 24.6? So these are pretty high odds because that's where like our mean and standard deviation lie. That's where most of our data is. So kind of understanding distribution. Okay, so binomial type thing. Okay, let's try number 2 out. So examples. So tires from this tire company are traditionally 5% defective. A truck carries 10 tires, 8 in use, 2 spares. If 10 tires are chosen from Apex, what's the probability that not more than 2 defective tires are chosen? So let me just write this as a probability of our event first. So the probability of our event, not more than 2. So I'm kind of, so like less than 2. So like a 0, 1, or yeah, just 0, 1. So less than 2, right? Not equal to, not more than. Yeah, not more than 2. So 0.
It could be 2.
Huh?
Because it just wouldn't be more.
I guess that's right. That's true. Yeah, doing the teacher thing of making y'all correct. Good job. Let's see, did I do that on my key yesterday? The other day? Yeah, I did. Okay. Yeah, we're right. See, I wrote it out like this. Sometimes that makes sense. You can see it over there on my key. When you look at it later, I like wrote out what that means, like 0, 1, or 2. Okay. So first things first is let's prove. Let's see what we're doing. How would I do this? So since we're doing binomial, you would think about this, but things that tip you off if this was like the AP test is I kind of have a fixed probability and I have a fixed number of outcomes and I'm asking a certain probability. Those are things that like when we're not doing all the same problems on one day, like when you're doing this in April and May, is like things to look for to trigger you off the binomial. So let's check and make sure. So did we check off our bins? So let's see. We're looking for defective tires or working ones, or are they defective or not, basically. let's see, so are 10 tires less than 10% of all tires made from that place? Probably, yes. So that's like a check. Check that one. We did have a fixed sample of 10, and we have a continuous probability of 5%, 0.05. So this is binomial. Alright, so it's binomial. I've got what I'm actually looking for down over here with my question. So then binomial distribution, it is a cumulative, so more than, so that's going to be our cumulative part, or less than, or equal to, I mean. And then, let's see, where is it? Yeah, it's n first. So n equals 10, p equals 5%, and then it'll ask you for lower and upper. Let's see, the lowest value you're looking for is 0. The biggest value you're looking for is 2. Oh, dang it. I should have done the mean and standard deviation first, so that we could see our guess. I knew yesterday, I like mentally said like, that thing is low, but I need to remember to do that one first. But, oh well. Alright, so we'll just check that one later. Because I kind of want to see the mean. Like, we could do it real quick. So, like, the mean is number times 10. So, I'm expecting 5% of 10 tires to be defective. So, what is that? I expect over the long haul that 0.5 of a tire to be defective. So like a pretty small, so we're probably, this distribution is probably going to be a pretty high probability. Like we should be in the low range of defective tires. Which, let's see, what did I get yesterday? Not yesterday, Tuesday. 98.8%, 0.988. Does that sound right?
Mm-hmm. Yep.
I got that on your calculator. You need to be able to do it on your own.
Should we do 3 decimals or 2?
I do 3 because then that gives me like, that's the same thing as 98.8%. That's what that means. So then it gives me a little bit extra because like 98 or 99 would be kind of, I feel like, too big of a rounding. Okay, so that makes sense. Like a ton of our defective tires are going to be in the low. There's not going to be a lot of like 3 or 4 or 5 defective tires in a 10 bunch. So that makes sense. Always check to see if your probability makes sense. So we already did that. That's our mean. Standard deviation. So just from the formula is where I'm getting those. Standard deviation 6 times 80% times 20%, whatever.
Wait. Well, not the same one as last time.
Yeah, that is. That's totally not right. You know, checking y'all. Y'all are paying attention over there. I don't know why. My brain.
Everyone's kind of like, except for you, Caitlin's like. Wait, it's the last one. I wrote down the wrong way.
All right. Yeah, so y'all wrote that. That's embarrassing. Okay. That one. And what do we get? Sounds believable. Let's see. Yeah. So I guess,
Nice.
yeah, 0.689 is what I wrote, but yeah, 6.9 is fine on that one. Cool. Cool. So what that means is we expect about out of 10, if I did many trials of grabbing 10 tires from this company, we expect about half a tire to be defective. And then plus or minus typical range, like a lot of our values lie plus or minus 0.69 from it. So in that 0 to 1.5 range, or 1 range, is where most of our defective tires would be. So that's pretty good on the tire company. You know, not a lot. They're pretty reliable. Okay. Alright, so this is going to be our assignment for the day. I'm going to do this one. There's this number 3, and there's 4 more problems on the backside. We still got. I'm going to do this one with you though. But like, if you feel comfortable with it, you're free to like run wild with it and just keep going. So this is what we're going to turn in on Schoology or anything. So let's do this one. If you have already looked at it, or if you haven't, let's look at it. So studies indicate that 70% of families of Bluebell, both the husband and wife work, which I'm pretty sure this is a town that they're referring to, not like the ice cream company. If 7 families are randomly selected from Bluebell, the town, what's the probability that blank? Exactly 4 of them work, more than 4 of them work. Alright. So I'm seeing studies indicate a certain probability happening all the time. I've selected a certain number, and I'm asking for a probability of 4 out of 7, more than 4. So I'm going to check and see if I can use binomial first. You do need to show your assumption. You do need to show that you can use it. So you write this out. Just BINS. Just real quick. So I guess what we're looking for, the event is, do both the husband and wife work? And do they work, or I guess we're just, if they both don't work, if one of them works, that's just all grouped into this other pile. So that's our 2 outcomes here. Do they work, do both of them work, or not is the option. So binary is both work, and then or not. Like we don't even care about the other outcomes. It's this outcome or else is what they've indicated to us in the problem. Are the events independent? So this is always where you have to assume is, do you think that 7 is less than 10% of couples in Bluebell? So do we think that there's more than 70 couples in this town? This is, you have to assume, we have no idea where Bluebell is. So, I don't know. Hopefully it's not like, I'm thinking of like a small town, like, does Franklin even, do they have like, is, maybe they have more than 70 couples there. I don't really know how big. That's pretty small. Anyway, so we're just gonna assume this, okay? That Bluebell does probably have, let's say it's a great big city. Probably not, but 70, more than 70.
It's like Brenham size.
Brenham, yeah,
Bluebell,
there you
yeah.
go. Yeah, Brenham. Great city of Brenham. Alright, is our sample fixed? Yes. And they're like it says, they're assuming, they're guessing, studies have indicated that the probability is 70% chance of it happening. So that's that's the odds they're giving for every single couple that they come into contact with. So that's the same probability throughout. Alright, so I am gonna do it this time. Okay, let's check our mean. Let's just see like where we expect our average. So the average is, out of 7 couples, what's 70% of 7?
4.9.
Yeah, 4.9. So you don't have to write it in words, but just understanding what that means. That means 4.9 out of 7 couples in Bluebell both work. That's what that means. So on average, if we did many samples of 7 from Bluebell, 4.9 out of those 7 couples would both work. Standard deviation is 7 times 70% times 30%. 1 minus 70%, 30%. Square root it. Yeah. Is 1.2. Can't remember if I rounded that. Probably did. 1.2.
Yeah.
So we expect 4.9 out of 7 both work, but it can deviate a typical amount. A lot of our values are plus or minus 1.2 from that number. All right. So that's our setup. So we're asking, what's the question, what's the probability that x equals 4? It's probably going to be a decently high number because we expect 4.9. So it should be at least 10, 20 something percent. It's probably not 5%. So we've proven it's binomial. And then equals 4 is a PDF. So equals 4 is an exact t distribution. N equals 7, p equals 70%, x equals 4. So let's see. 0.227. Did y'all
Yeah.
get that one? 0.22. So 22.7% chance of that happening. Hopefully we aligned on that. Alright, and then one more probability that more greater than 4 work. So 5, 6, 7 couples work. So more than 4 CDF. Show your work. N equals 7. P equals 70%. Lower, upper. Let's see. The lowest value is 5. Greatest value is 7. Always be careful on your CDS. That's where you can make a mistake. So make sure it was 5 there. And 0.647 should be right. 0.647. Alright. So those numbers seem to make sense. 64% were more than 4 working, both couples working, which looking at our average and our standard deviation, it makes sense. So checking yourself, doing those. So just gave you a bunch of problems to try out. So there's number 4, 5, 6, 7. So you got 4 more problems I want you to do. You can check the key and you can just get into a good rhythm like when you do a bunch of these.
So we can't turn these in paper?
You can turn those in paper or you can turn them in
Are
on.
you gonna Lysol them again?
Huh?